The broadcast is now starting. All attendees are in listen-only mode.
Hi there, good morning everyone, and good afternoon to everyone joining us from South Africa. Sorry for the delay there. We had some technical issues. So I just wanted to remind everyone that you have the capability to raise your hand if you're having some type of a technical problem. And then also on the in the panel, you can write questions and we can take those at the end. So Mark, do you want to introduce our panelists for today?
Good. I'll make it very brief. I want to tell you how pleased I am that Jessalyn Brown is able to join us. Jessalyn is a research geographer. You've seen probably that short bio of hers at AROS, which is the outfit that manages the Landsat imagery. And the only thing I wanted to say is that Jessalyn is responsible for a really important program in the USGS, and that's LCMap. And I say it that way because I believe it's truly one of the big breakthroughs that's happened in natural resource business, and that's this idea of being able to basically mine the information of the 30-plus year archive of imagery that has been acquired with the Landsat constellation of satellites. And so anyway, this is Jessalyn's responsibility. There's no greater expert on the topic in the country, and I think it's our example, the USGS's primary example of machine learning and big data. So with that, Jessalyn, thank you again for joining us.
Thank you, Mark. Thank you for such a great introduction. I hope everybody can hear me after we had mic problems earlier. So I am going to try today to give you an overview of this new work that we're doing called LCMap, which stands for Land Change Monitoring, Assessment, and Projection. And I'm actually leading in by showing you an animation of our primary land cover layer. Actually, this is a land cover change layer because anywhere you see the purple flashing on this, that is a annual change in land cover as shown in our prototype data. So all the data I'm going to show you today is prototype because our operational system is still running and we don't have all of the data out of that yet. Other things to say is this is, as Mark mentioned, this is from our US Landsat satellite series of satellites that have been orbiting the Earth and collecting data actually since the 1970s, but this particular project is using data from the Landsat 4 era onwards, the Landsat 4 instrument, which was launched in the 1980s. And this time series starts in 1985 and ends in 2017. I don't remember if 2017 was skimmed off or not. Sometimes we end at 2016 because the data are more stable with that year with this run. So this particular part of the world is the Columbia Basin in Washington State of the United States, which is in the west, and what we're showing here through time where these purple flashes happen is land change. So the landscape is changing. Dry land, cropland is shifting either back into grassland, shrubland. You can see where some square fields are being cropland is heading out of there and it's turning into more of a grazing situation. And there's also an increase in irrigated agriculture shown in the center pivots that are flashing up purple through this time series. We also have a bit of urban or developed growth in the cities shown in this window. Anyway, I like to start with an animation to show you what the capability of LCMap is to pull out change. This is just one of our layers. Primary land cover is one of our data sets. So I'm going to, give you a overview of the Land Change Monitoring, Assessment, and Projection Initiative. And Mark was very kind at saying I'm very important leading that. I just really call myself the LCMap NAG. It's my job to keep the team moving forward, and I have a wonderful team of people working on this. This takes probably more than a village to make this happen. So the LCMap vision, this work was launched several years ago with a research approach. A particular researcher, who I'll talk a little bit more about, had determined that we could extract more out of the Landsat record than we were doing. And as Mark also mentioned, this really does represent machine learning and using big data sets to provide information. So the vision that we're trying to march to is going from data to answers. We want to provide documentation and understanding of historical land change through this record and contemporary land change as it occurs. We're not quite to the second one yet, but we're heading in that direction. Provide ongoing answers to questions on why and how the landscape is changing. And why is that important? It's in order for us to explain how past, present, and future land change affects society, natural systems, and the functioning of the planet. So we're focused on providing these basic building blocks of information on how the land surface is changing. And land cover is a component of what we do. It's not the only focus. We have a vision to alert relevant stakeholders of important or emerging patterns of land change and to support users of land change data in their applications and partner with them. These are all things that we're striving to do, utilizing this very rich Landsat record that we have, this satellite record. So we think of LCMap as being the next generation in land change and land change science and land cover. I have a team member that likes to say, well, this isn't your grandmother's land cover. It builds on a rich USGS ARRO's history of land change research and development. And, I didn't mention this earlier. I work for a center called the Earth Resources Observation and Science Center in the center of the US in Sioux Falls, South Dakota. And we have been the home for Landsat operations and data for a long time. We also do a number of other science and engineering tasks here, but really Landsat is kind of our main, our main show, if you will. And we're trying to respond to a ever sophisticated, growing sophistication in our users. It used to be when I first started working here 30 years ago, doing things across the nation in one fell swoop. Creating products or doing monitoring was a difficult thing to do, and we didn't tackle it with Landsat. But now we have better systems, faster computers. This allows us to explore how the landscape is changing over larger geographic extents using much more machine learning approaches, to do it over longer time periods with faster turnaround at higher resolutions, and to integrate information on cover and change. And I'll talk about that a little bit more. So these are things that we want to respond to these demands in the science community. And USGS is a part of our Department of Interior, so we're interested in providing other bureaus in the Department of Interior with information. That would be or USDA's Forest Service. It's really all about kind of a wall-to-wall look at how the landscape is changing. Foundational elements, and I'll talk a little bit about all of these, include what we call our Landsat Analysis Ready data, which is like a data cube. And I don't know if you guys have heard of this. I know there's an activity going on to create an Africa data cube right now. So this is where, when we collect data through time and with different instruments, it can create technical difficulties for doing land change. land change, really an elemental part of that is that your pixels line up through time. And, I won't be going into the details of how that's done. There's a lot of depth to that, technical details to that. But, it's a foundational element. We need to know when we look, when we ingest one pixel, 130 by 30 meter block of data through time, that we're looking at the same place. Otherwise, we're going to be detecting things or producing data for spurious change. It's not the real deal. So that has taken actually quite a bit of effort on our part. There's a lot of heavy lifting. So we also, foundationally, we want to create land change and land cover derived from all available Landsat. So we're not throwing data away, except for, we don't use the clouds. Clouds are not useful for this activity. But in the past, we weren't really taking advantage of the whole archive. And then another foundational element that I'll talk about a little bit is our independent reference data, in order for us to provide validation of our products as we produce them. And so, underlying this whole thing, and actually everything we do at AROS, is that we get better eyesight from space. We can see across the world with these instruments, and there's a number of different instruments up there, and this won't be an exhaustive study because we're focused on Landsat. This particular example shows an ICONOS image on the left, which is more of a higher spatial resolution but lower temporal frequency kind of mission, but gives a huge amount of detail. And since humans are changing the environment, we really want to know what's going on. So as I said, the Landsat ARD is a huge resource for us, and this kind of shows this very long, now certainly close to 40-year, not quite, record back to Landsat 1, which was launched in 1972. And as I said, we're using data in this project from Landsat 4 onward. Data frequency is a huge, that's our currency. It's a huge part of this project, where we don't have enough looks, we don't have enough overpasses in data collection. That causes some problems to our approach. And unfortunately, we don't have a time machine. We can't go back and collect more data for those places. So this is kind of a flashing back and forth. This is kind of the way we used to do things, and it's still useful to do. We call these change pairs. So you're looking at one period and another. In this case, it was the event that happened was a wildfire. What's shown in black is a wildfire, and it impacts the surface reflectance of this Landsat scene where the wildfire occurred. Everything looks black. And this is an abrupt change. This is a fairly large wildfire. I have lost track of the name of it, but maybe that's not important. And we used to do this work where we would just compare the two. And, this is kind of what we're working away from in LCMap. It is useful to do a change image and show the area that has changed, but we can do so much more. And we're trying to get at land surface change. And these are types of change, natural change and anthropogenic change, that we can get at through LCMap. So, and through using the whole archive. So, all of these, assuming that there is some sort of surface reflectance signal through time that shows change, we can capture things like fire, trees falling down, a slower process, which is forest succession. Fires are more of an abrupt change versus a sort of a long-term slower change. Our techniques kind of focus more on the abrupt changes, but we're working on how we can improve this to detect slower changes as well. Conversion to agriculture and conversion to development, those conversions would actually represent a land cover change, whereas shrub encroachment might just be a a land surface change that doesn't trigger a cover change, and we sometimes call that conditional change. So that kind of sets the stage for the kinds of changes that we're trying to detect. And again, I said the ARD was foundational to us, and I won't dwell on this too long, but this is the representation of reconditioning of the Landsat archive. So it's so that the pixels are nicely stacked up. And we do a lovely job here on, focusing on geometric registration and accuracy. We also do radiometric processing to top of atmosphere. This is all very geeky, and I'm not sure the background of the folks who are listening. So, what we're interested in is the best data we can work with that will eliminate problems due to misregistration and also problems due to atmosphere that could cause a false signal, a false change signal, and other things as well. So we pack our data into these 150 by 150 kilometer tiles. There's 428 of these tiles across the United States, and we're working across the country tile by tile to detect change. The first step was creating the ARD. The next step is having the code to detect change. After we detect change, then we do a classification process to pull out the land cover information. And I won't go into this in a lot of depth, but inputs matter. So we actually do have an archive that has varying data richness, or as I would maybe call it, data frequency. So the number of pixels through time is going to vary where you are in the United States. And this particular one just represents what we get when we have, so this is due to orbital characteristics of the Landsat series of satellites. So they come around through orbits. Our orbits overlap. And in the red areas, you have higher numbers of observations because as your satellite orbited, as Landsat orbited, there were overlaps, and we looked at pixels. Often these are within 1 day, and in the middle where we have lower pixel richness, we have to sort of make sure that our change detection is robust enough to detect even change. And we've explored getting rid of data, but that kind of goes against the grain. So we're using all of the pixels that are good quality. This doesn't show the good quality pixels. So what is LCMap, and what do we use for our approach? We are using an algorithm called continuous change detection and classification. It was published by Zhu and Woodcock. That reference is shown there back in 2014. And really the idea to do this across the nation was hatched very shortly after this publication came out. And it's taken a long time for us to get to where we're and I'm always, I'm ready for us to be operational because we want to move on to the assessments and the applications part of our work. But right now we're still producing data. So again, this is based on analysis of the time series of available cloud shadow-free Landsat observations from Landsat 4 to Landsat 8. As we, Landsat 8 is a relatively new instrument. We're working in the building and outside of the building on what Landsat 9 is going to look like. That is the next instrument in the series. But right now we're through Landsat 8, and we have this CCD. The approach is called CCDC, but the last C is classification. So the change detection capability is something that allows us to look at, identify pixels that have either had a land cover conversion, for example, like that grass to crop conversion, or conditional changes, for example, like forest thinning or insect outbreaks where the cover doesn't change. The cover type is still forest, for example, but an event has happened and we got to change. And it has the potential for near real-time change detection. Now, real-time, actually I should have changed this slide to say rapid. That's my preferred way of determining this, or actually the terminology I prefer to use. this is also something that we're working on right now. So I'd like to show this slide that really is the essential look at one pixel and what does one pixel do through time. And over this example, we have a pre-fire, a forest situation where it was healthy, everything was going fine, then there was a fire, and then we had some post-fire recovery, and it continued on. And the lower chart shows the behavior of that pixel, the reflectance of that pixel in the ARD in the mid-infrared band. So we base our change detection on bands green, red, near IR, shortwave infrared. We don't use the thermal bands or the blue band to determine change. And in this example, we see an abrupt change around 1994, and we see two models. So CCDC develops, goes through all these observations and establishes harmonic models that represent the, the condition of those pixels through time. There's a seasonal component to that model. There's a trend component to that model, and I'm forgetting the last. It's three different model components, and I'm forgetting the third one right now. I apologize. I advise going to the Jeju reference for more information. So our methodology, so we take this information at those models. The black dots represent sort of the full gamut of what we're getting over those pixels. And the green line and the blue line represent some really nice, more informative data to help us identify change and cover. So our change monitoring and land cover mapping is based on this algorithm, and we use all these observations to train the models, to develop the harmonic models. Down at the bottom, I'm showing another example through time where we have two different models shown in red and green, and a break in between. So we calculate these time segments, these time segment models for each pixel, and then determine the breaks. That gives us information for when a change happened. And then we extract that information on change and classify the time segment into products. And these products right now are being created on an annual time step. They could be created on a higher time step, like seasonal. Seasonal information could be pulled out of this. We have not climbed that hill yet. So the first goal is to create the annual data and move forward with that. We have a study has been done related to people's users' desires about land cover data, and the most common time interval that was requested in this study is annual. And then at that point, we have all of these change coefficients for each pixel, and we use the XGBoost, which is a regression tree classification tool, machine learning classification tool, to derive the thematic information, the land cover information, and generate maps. And what you see on the right is an example of one of our data sets. Although you've already seen some data because I showed you the animation at the beginning. So we're for this annual time series, these annual products that we pull out from the CCD models, we're creating 5 products. This is what we're calling our version 1 LCMap. The products on the bottom, change day, change magnitude, time since last change, spectral stability, and model quality, are for the most part extracted directly from CCD, the change detection algorithm. And they refer to units of time, honestly, except for the change magnitude, which is an indicator of the amount of change that occurred at a break. And then the top 5 are the land cover that are extracted after the XGBoost, or the top the top 5 are extracted from XGBoost after we classify the time segments into cover. And we use the National Land Cover data set to provide us with training. We need a large amount of training data to create these cover classes. And XGBoost, you know, because it's a kind of a tree process and it has a boosting, can give you land cover at the primary confidence and the secondary confidence. That's due to this XGBoost process. And then the last product is land cover change, which is really derived from primary land cover over time. So change is determined as being a location where an actual land cover change has occurred. And what we are discovering and what we know is that change across the landscape is more than just thematic land cover change. It's, you know, and I gave you that table before. There are other changes occurring. So this is just another look at that series of products and the descriptions. And this is all found on, sorry, I didn't put the reference here, but we just had a paper published. It's in press right now in Remote Sensing of Environment on the lessons learned in implementing LCMap. So that's also available for people to leave. So as I said, you know, we know these are just also some pictures of thematic and non-thematic change. Most of these are thematic change, but the forest planting and harvest might be a non-thematic change, depends. Post-fire recovery would lead to probably a thematic change. When the fire happens, you would have a break in the model, and then you would have something new growing up, which would not be forest or tree cover at that time. It would start out as grass shrub. And insects and disease can be a non-thematic change. So we're trying to capture all these different kinds of change in our process. So let's see if I can do another animation here. All right, so this is a prototype, an animation of our prototype data in the lower Mississippi floodplain, where there's a lot of coniferous forest plantations, like pine plantations that are planted and then harvested in these large blocks at different times. So the green dot is represents you know, the time series on the right. Those time series are collected at that green dot. And in this case, I'm showing you the red, the near IR, and the first shortwave infrared band. And what's shown in different colors are the breaks that were extracted from this time series. And a major break happened. Hang on, I gotta start it again. This one doesn't start as cleanly as I'd like. Sorry about that. So in around 1988, that patch where the green dot is experienced a cutting, a harvest, and then as we go forward in time, it starts to fill in and the forest starts to grow. So this is kind of the cycle of forest harvest and forest regrowth over plantations as captured by LCMap. And also we asked the question, and right now I'll just say I'm not showing you national results because we just don't have all the data yet. We're in the process of producing it. But you know, we like to show these things called land change stories. So can LCMap monitor and help quantify hurricane damage in the Florida Everglades wetlands? So we have in this example a number of different events that have happened, and I really pulled out for this case major hurricanes such as Katrina, which actually did hit Florida before it came around and went back north and hit New Orleans. And it was a lesser hurricane at this time. The category ratings of the winds of these events are shown in the graphic as well. Excuse me, I'm pulling out my notes on this. So this is all you know, different wind directions, whether a hurricane came from over land or over water, which leads to differences in storm surge and things like that happen in these events. But all of these major hurricanes are detected in LCMap. 1992 is when Katrina and, hang on, I got to remind myself, Katrina and Wilma came, or excuse me, 1992 is Hurricane Andrew, Katrina is in 2005, and Irma is in 2017. And so these are two examples of our products that people haven't, you know, they're relatively new. And because CCD can now produce this information on land change, now we can use it to, on the lower row, determine when the date was. And although you can't read the axis on these, and I'm sorry for that, the higher spikes really show the amount of damage, like for example in 1992, the amount of change that was identified for disturbance that occurred at this point in time. And there were multiple events in 92. There was more of a singular event in 2005 and a singular event in 2017. And the extent of the damage is shown here, and then change magnitude also shows the same pixels that are identified in change day of year, but it's a measure of the amount of change at that spectral break between two models. And what I want to point out is that this did not result in a land cover change. So this is all within the wetlands, the mangrove and sawgrass wetlands in the Florida Everglades. So as we classify these results, we don't see a thematic change, but we definitely see change in the landscape. I'll go past this example. So in this case, LCMap change monitoring produces compelling information on annual land change, but it's not always land cover change. And what we're finding in looking at our prototype data, that we see a lot more spectral change than we do see land cover thematic change. And we're working towards this rapid change detection capability. It will still need some time after an event to truly detect a change and not be hampered by detecting false change. But CCDC, a different algorithm might allow us to analyze breaks in the ARD time series. So I'm shifting over to talking about our accuracy assessment. And we've collected independent reference data for 25,000 randomly sampled points across the conterminous US in a joint effort with the US Forest Service. And this reference data collection had to start much earlier than we had land cover products. It's designed to help us produce area estimation and error, statistical error for all of the land cover that we are producing in LCMap. Right now, we have finished the data collection. It took us 4 years to do the interpretation for these points, maybe 3.5 years. But we have this record now, and we're using it for evaluating land cover and change across this record. We're also investigating whether we need to intensify the sample as we go forward. But our goal this year will be to release the data and release it with accuracy numbers associated nationally and by region. And this data collection is based on a joint USGS-US Forest Service response design that was produced in 2016, that was published. And we're collecting 5 variables over about 30 years, and we're increasing the years right now over those 25,000 plots. And I can't say much more about this. This is probably, if there's interest, this is probably worth an entire presentation just on the accuracy assessment alone. We have an R&D component in our monitoring, and our goals for this are to improve and further systematize our change detection. I won't go into detail about that today. I'm over time actually. Research approaches for using different wavelengths and instruments. We want to intensify our record by using the Sentinel-2 data from Europe. and get more frequent looks on the surface in order to catch more change. We need to further improve our classification methods. There are some characteristics of the output that we're doing, at least at the early part of the record and the later part of the record, where we need to do some work on classification. The other components of LCMap, so the A and the P, the A stands for assessments and the P stands for projection. So really, why are we doing this? We want to actually be able to tell the story across the country of change and assess that change. What changed? Where did it change? And hopefully get to the why and what are the consequences of those changes in the future. We've done a prototype assessment of land change across the Piedmont. So we have produced data in a prototype system that is going to look just like our published data. And this area was investigated because we have a lot of, we produced a lot of data to cover a lot of the eastern seaboard of the United States. And what we're determining is that, at least in this region, changes is about a 2 to 3% of the area changes every year. There are some years that are bigger than others, and we need to investigate why. So there's some variability over time. I don't have the animation of this was way too big, and the granularity of the change was so small you couldn't see it. But what you see if you look over time is urban expansion and more of that changes from forest to ag, and actually from ag back to forest, because we have some areas in some places in this part of the country where agriculture is being replanted, and there's also some of this forest plantation activity. We're standing up an applications assistance to communicate and engage with LCMap user communities to do the following things. I won't read the slide for you. I don't have a strong example to present today. Again, another area that probably deserves a lot more discussion. So this is just a highlight. But we think our assessments and applications are really where the future lies. We do a lot of heavy lifting to create the data, but what's really interesting is working with the data and creating science results and applications, helping applications like looking at water quality and water quantity. This is a big area that we're exploring. And we've done some prototype studies of this so far. LCMap projections, the P in LCMap is the use of CCDC output to inform model projections of land cover into the future and backcasting into the past. So this involves model scenario constructions where we bring climate projections into the story, into the modeling, and estimate the probability of land patches. So this is done on a patch basis to change in the future based on future climate, or to change in the past based on past climate. And we get a spatial distribution for this. This activity using this model called 4C has been going on for years here, but LCMap will then provide a this annual look at land cover. And this is just shows kind of how we use the LCMap in the contemporary satellite era to estimate annual change, and the 4C is used for the future scenarios and the historical scenarios. Again, another topic that's pretty broad, and I won't be able to go into much detail, and it would be better to have Terry Soul give this presentation. So just getting close to wrapping up. Sorry, I went over. Hopefully that's not a problem for anybody. So this is our status slide and what's next, and this is very high level. We're working really hard to complete our data production for the conterminous US, so the lower 48 states of the US, and release our version 1 data. We're hoping that's going to occur later on this year. We have hit I'll just be very frank, we have hit a lot of technical challenges with this. We are ingesting huge amounts of data and producing fairly large amounts of data, as you might imagine. These coefficients that we produce for every pixel across the country are fairly deep. These are like, you know, these are floating point data. There's just a lot of it. For every tile, we have approximately a terabyte of data that we're reading. And then I can't give you the amount what we're writing out right now, but it's just a lot of data. We also have stood up a system in-house versus doing this on the cloud. We're facing doing this on the cloud in the future with data volumes. Throughput or I/O for this process is immense. We're going to perform and document our accuracy assessment and produce that as we release the data. We have a plan to perform a baseline assessment. So what we did for the Piedmont will roll out for the entire country and produce a comprehensive land change story. So how is the landscape changing, when, where, and why? We'll do a true launch of this applications assistance facility. It's hard to launch this until we have all the data ready to go. And as we get data out through 2017, we have to turn around right away and produce data for 18 and 19 and get our annual forward processing stream going. The projection work will continue and get going in the next 12 months. We're working on improving our classification methods where we see, you know, we'll learn a lot from our initial accuracy assessment where we have to change things. And we've been asked to develop and implement our process for rapid change detection for communities such as the fire community. So those are all the things that we have on our plate to do. And since this is an international audience, I do want to mention that CCDC as an algorithm is also being implemented on Google Earth Engine. So that's a platform where you can, where users that are versed in using Google Earth Engine can use their tools to analyze all kinds of satellite data. But yes, the Landsat archive is also in there, although it's not exactly our ARD data, I don't think. I can't tell you exactly what's in Google Earth Engine. That's not my expertise. But LCMap is focused on the US. The capability is coming at some point. I know they're working on it right now to be able to run the CCDC on Google Earth Engine. I understand from the folks who are doing this that they've discovered that it's an intensive processing, and we could have told them that uses a lot of resources, even on that cloud platform. They saw an influence from running CCDC on Google Earth Engine performance. So stay tuned to news on this capability. I suspect if this audience wants news on that, I can help find someone who could talk about even some activities where they're doing testing over Africa. I don't think it's South Africa, but you know, wherever there's Landsat data or wherever there's satellite data, there's a possibility to run this. Image frequency could be an issue in earlier years of the record, and we're extremely spoiled and fortunate in the United States in terms of how much data we have to work with. The data collection through the Landsat history has been affected by a number of different sort of political. There was a time period where Landsat was commercialized and people had to pay up front to collect the data. And as you might imagine, there was less data collected, both in time, you know, periods of time, and actually across space, because the data was, it was not a good idea, in my personal opinion, to commercialize the Landsat at that point back in the 80s. And so we have less data. You know, we can't really produce change unless we have the data to support it. We've released our sample data. So we have a sample tile, prototype results, all 10 products through the time series over a tile in Southern California. And this is available for people to download and work with. We really want to get some feedback. We're doing a workshop on this later in the fall, and we'll need to, you know, this is in person at a conference, the PCORA conference, but we'll try and figure out a way to get a video done of that training. it is not exactly like working with just regular land cover data, because there's a wealth of information available here, and we need to help people use these data sets in concert with each other and help them figure out how to pull out the information that they need. And at this point, I have another animation that I'm showing. You've seen one of these. This one is over a different landscape, a forested landscape and urban. This is Rapid City, South Dakota, and these are the Black Hills. Most of the change that we're seeing in here is developed growth over the city over time, which is not a hugely growing city, but you can see it happening. And some fire scars that appear, especially in the later parts of the record. And with that, I will give you some contact information, and I'll close up and take questions if there's time.
Certainly. I'm going to give people a little bit of time to enter any questions that they may have, because I haven't received any quite yet.
Yeah, so this is sort of, you know, I know that you all are interested in water applications, and this is kind of, you know, an indirect look at how you might use these data for water. I didn't really go into that in depth, so might be something that we can expand on later.
Okay. Well, seems like we're not getting any questions, but it was really informative, so thank you for that, Jessalyn.
Well, thank you.
Okay. Mark, did you want to sign off today? I'm going to take that as a no. Oh, there he is.
I was muted by the organizer.
Oh, I apologize.
Okay.
It's hard for me to ask you a question and then unmute you.
Right. Yeah. Okay, I'm good. I'm back. No, just want to thank Jessalyn for putting together this presentation. This is obviously a very complex subject, but I know that some of the partners in Africa are interested in this idea of potentially doing some of this work themselves, and so there probably will be some follow-up on that. They do have a collaborative partnership with IBM as well, so I don't know if there's a linkage that can happen there, but anyway, yeah, it's I was also going to mention one other thing real quick, and that is that there is some work going on in both Kenya and Ethiopia under an USAID cooperative project with the USGS, and they're using remote sensing to look at groundwater, places where groundwater is surfacing, and so this could actually be very useful for that. So it is, maybe some of you know Saud. You probably know Saud, Jess. I think he was at Eros at one time. Anyway, so they're using, you know, Landsat imagery to map groundwater evidence at the land surface in Kenya and Ethiopia.
I do have, I received one question. I'm actually going to give the mic over to the individual that asked this question. Rodolfo, do you mind? I've unmuted you. Do you mind asking your question?
Yeah, thank you, Liz. Hi, thanks for the presentation. I have a question with regards to water bodies. I wonder, you know, I think of interest, at least in Africa, would be to look at historically how, you know, we have some streams that are perennial and some streams that are intermittent, and they go dry as part of the year. And I wonder, or water bodies, you know, I wonder if with this program would be possible to look at trends in how some of the streams go more dry or water bodies.
Yeah, so I recently have been looking at a time series, and I didn't bring it into this presentation, over a pretty large reservoir in California that was in that sample data. that we put out, and we definitely saw shoreline changes in that water body over time. So I think the question would the ability of this technique to detect change would really depend on the spatial amount of change. So for a small stream, you know, these are 30 by 30 meter pixels. So I would say small streams would not, this would not work for that unless you had a higher resolution instrument. And then the problem is you don't have those data back through time. Like you might be able to get 10 meter or 2 meter data now from a commercial, well, you can get 10 meter from Sentinel-2. Sentinel-2 is a similar instrument to Landsat, except it doesn't have the thermal, and it has a 10 meter, you know, an ability to resolve a 10 meter by 10 meter change, if you will. So you might be able to use this technique either with Landsat for larger water bodies or with something like Sentinel-2 for smaller water bodies and detect change. So, you know, I would recommend that if you're interested, I don't know what your bandwidth is for downloading things, but all of the data are all zipped up, and you could download that sample data. Here it is. Here's our address for that. And actually, if you just type LCMap, you'll probably come up with our website. You could see this, the water body I'm talking about is kind of in this upper quadrant, you know, to the right of Fresno here. We could see changes in that water body. So sorry for the long answer. I think there's a potential.
Okay, thanks.
All right, that looks like all the questions we have today. Just double checking. Okay, yep. So thank you very much, Jessalyn, and I appreciate you speaking today and overcoming technical difficulties with me to
technical
make
and timing.
yeah, to make this possible.
Yep, no problem. I'm happy to be asked. Thank you.
Okay. Thank you, everyone, and come back next week for more webinars. So, bye.